this lesson, we'll be learning how to determine enthalpy changes using Hess's law. Hess's law states that the enthalpy change for the conversion of reactants to products is the same whether the conversion occurs in one step or several steps. Take this question for example. H2SO4 decomposes into sulfur trioxide and water vapor. We want to figure out the enthalpy change of this reaction. To do that, we need to use the information given, which are these three subreactions that overall lead to this equation. We are given the enthalpy changes of each individual reaction, as well as their mole ratios. Depending on the changes we need to make on the substeps, whether it's dividing or multiplying the ratios of an equation, or flipping the reactants and products, that will allow us to make the necessary cancellations and cross out any of the molecules that aren't present in the net equation. Any changes that we make to these subreactions, we will have to make the same change to the corresponding enthalpy change. Once we have all three of our enthalpy changes, we'll be able to solve for the overall enthalpy change of the net overall reaction. The first thing that I like to do when working on Hess's law questions is to find any molecule that only appears once in all of the substeps. In this question, those molecules are H2SO4 in the first reaction, sulfur trioxide in the second reaction, and water vapor in the third reaction. In this question, all of our reactants and products only appear once, meaning that everything else is going to get cancelled out. You'll see as we get further into the question. So now, what's the next step in turning these substeps into the net equation? Well, in reaction 1, the H2SO4 is at a 1 mole ratio, just like it is in the overall reaction. However, in reaction 1, it's a product and not a reactant. To change that, we must flip the equation around, making the reactants the products and the products the reactants. And for this change, we will write flip. As for reactions 2 and 3, the sulfur trioxide and the water vapor are both in their correct molar amounts, and they are both on the correct position of the reaction as products. So for these, we can just write an X next to each of them, showing that we're not going to make any changes. Now, because we have flipped the first subreaction, we must make the corresponding change to the first subreaction's enthalpy change. Instead of an enthalpy change of negative 235.5 kilojoules, because we flipped the equation, we must also flip the sign of this enthalpy, making it positive. And again, we made no changes to the two other equations. Now, before we calculate the overall enthalpy change, we need to confirm that our substeps are equal to our equation. So H2SO4, we can skip that because it doesn't appear anywhere else. Next, we have H2S as a product. Do we have H2S as a reactant? Yes, we do, so these cancel out. We have 2O2 as a product. Do we have 2O2 as a reactant? Yes, we do, so we cross it out. Skipping the sulfur trioxide because it doesn't appear anywhere else in the equation. And then liquid water as a product cancels out with liquid water as a reactant. And water only appears once. So under this, we can write our net equation. H2SO4 turns into sulfur trioxide plus water vapor. And then to find the enthalpy change of the overall reaction, we're going to add together 235.5 kilojoules minus 207 kilojoules plus 44 kilojoules. And then because this is adding and subtracting, we're looking at the lowest number of decimal places in a given value for the question, which would be 0 since we have 44 kilojoules with no decimal places, or the same thing for negative 207, meaning that our answer should be rounded to have no decimal places, making our final enthalpy change 73 kilojoules. And if we were to identify the type of reaction, this is an endothermic reaction since it gained a quantity of energy. Let's move on to another question. Here, our overall reaction is carbon dioxide gas decomposing into carbon and oxygen. Remembering our first step, we want to look for any reactants or products that only appear once, and that would be this carbon and this carbon dioxide. Since these two only appear once in the substeps and also appear in the overall equation, whatever changes we make to these, we must also make to their equations as well as their enthalpy changes, like we did in the last question. In terms of this carbon, it has a ratio of 2 moles, but we want it in a ratio of 1 mole. Since it is already a product, the only thing we have to do is divide the equation by 2. This situation is identical for the carbon dioxide in equation 3, where the ratio is 2 moles, but we want it in 1 mole. So since the carbon dioxide is already on the reactant side, we do not need to flip it, we just need to divide the equation by 2. Now what about equation 1? As you can see, water, hydrogen, and oxygen appear many times in these three equations, meaning that somehow all three of these are going to be cancelled out. But they must be cancelled out in a way that completely removes water and hydrogen from the overall reaction, as there is none present there. Taking a look at the water, the only other place that we can find it is in reaction 3, where it has a mole ratio of 3. However, let's not forget we divided the equation by 2, so it's really 3/2. What changes can we make to reaction 1 to make the waters cancel out? The water and the rest of the equation for substep 1 can be multiplied by 3/2 and flipped, making the water the same stoichiometric amount as the water in substep 3, as well as on the opposite side of the equation so that they can both cancel out. The reason why we'd flip equation 1 and not equation 3 is because we've already determined that all we need to do to equation 3 is divided by 2, because the carbon dioxide is already on the correct side, and if we were to flip it, we would put it on the incorrect side as a product when we want it as a reactant. So we simply just flip equation 1. As for the hydrogen and oxygen, they'll most likely cancel out nicely. The only way to know is to actually try and see. Now, once again, whatever changes you make to the equations, you must also make to their corresponding enthalpy changes. So since equation 1 was multiplied by 3/2 or 1.5, as well as flipped, we need to take its original enthalpy of 643 kilojoules and multiply it by -1.5 to give us -964.5 kilojoules. And then for reactants 2 and 3, we're just dividing these answers by 2, giving us new enthalpy changes of 95.3 kilojoules and 1755.55 kilojoules respectively. Now for my favorite part, canceling out reactants and products and seeing if we did the question correctly. So first, we have 3/2 hydrogens as a reactant. Do we have 3/2 hydrogens as a product? Yes, we do. So they cross out. Let's get the oxygen from now. We'll come back to it. Next, we have a 3/2 water as a product. Do we have the same thing as a reactant? Yes, we do, so they cancel out. We have a half ethane as a reactant. Do we have a half ethane as a product? Yes, we do, so they cancel out. The carbon and the carbon dioxide stay the same because they only appear once. And now coming back to oxygen. On our reactant side, we have 3/4 oxygens, and on our product side, we have 7/4 oxygens. Now, this whole time, whenever we cancel something out, think of it as one side being the positive of a value and the other side being the negative of a value. Adding them together would equate to 0, and so they can cancel out. For here, it's not much different. We're just taking this 7/4 and subtracting the 3/4, and just subtracting the numerators. 7 minus 3 equals 4/4, which equals 1. Now that we've determined that, we can cross out this 3/4 oxygen and cross out this 7/4 just to show this 1O2, making our overall equation, carbon dioxide decomposes into carbon and oxygen gas. As for our net enthalpy change, we once again want to add all of our individual enthalpies and round our answer to the correct number of decimal places, which in this question would be no decimal places thanks to the 643 kilojoule value, making our final answer 886 kilojoules, also making this reaction an endothermic reaction, since it gains a positive amount of energy. Here's a practice question that you can try yourself. If you can get this on your own, I would say that you're good with Hess's law. The answer will be posted at the end of the video. If you've made it this far into the video, chances are you're learning a lot and enjoy the content. So if you don't mind, consider subscribing, as it shows me that you like what you see, which helps me post more videos. Anyways, that's all for now. I hope you have a wonderful day.